The solar system comprises 8 planets, more than 400 natural planetary satellites, moons, and countless asteroids, meteorites, and comets. There are 8 planets in the solar system. The 4 inner terrestrial planets are Mercury, Venus, Earth, and Mars, all of which consist mainly of rock. The 4 outer planets are Jupiter, Saturn, Neptune, and Uranus, giant planets that consist mainly of either gases or ice. Pluto was considered the 9th planet until 2006, when the International Astronomical Union voted to classify Pluto as a dwarf planet instead. More than 4,500 planetary systems have been discovered. Astronomical surveys have found that stars usually have planets, and thus there would be several 100 billion solar systems in the Milky Way galaxy. The hottest planet in the solar system is Venus, which has an average surface temperature of 464 degrees Celsius (867 degrees Fahrenheit). The longest a landing probe has landed under such conditions is a little more than 2 hours. Scientists have multiple theories that explain how the solar system formed. The favored theory proposes that the solar system formed from a solar nebula, where the Sun was born out of a concentration of kinetic energy and heat at the center, while debris rotating the nebula collided to create the planets. Europa and Enceladus, moons of Jupiter and Saturn respectively, are ice-covered rocky objects that scientists think may harbor life in the water beneath the surface. Some geological evidence points to the possibility of microorganisms on Mars. The solar system is the gravitationally bound system of the Sun and the masses that orbit it, most prominently its 8 planets, of which Earth is one. The system formed about 4.6 billion years ago when a dense region of a molecular cloud collapsed, creating the Sun and a protoplanetary disk from which the orbiting bodies assembled. The Sun accounts for 99.86% of the solar system's total mass. Inside the Sun's core, hydrogen is fused into helium, releasing energy that is emitted through the Sun's photosphere. This creates the heliosphere and a decreasing temperature gradient across the solar system. The next most massive objects of the system are the 8 planets, which by definition dominate the orbits they occupy. Closest to the Sun in order of increasing distance are the terrestrial planets, Mercury, Venus, Earth, and Mars. These are the planets of the inner solar system. Earth and Mars are the only planets that orbit within the Sun's habitable zone, in which sunlight can keep surface water liquid under atmospheric pressure. Beyond the frost line at about 5 astronomical units, are the planets of the outer solar system, 2 gas giants, Jupiter and Saturn, and 2 ice giants, Uranus and Neptune. Jupiter and Saturn possess nearly 90% of the non-stellar mass of the solar system. Objects of planetary mass that do not dominate their orbit but orbit the Sun directly are called dwarf planets. The International Astronomical Union's Minor Planet Center lists Ceres, Pluto, Eris, Makemake, and Haumea as dwarf planets. 4 other solar system objects are generally identified as such: Arcus, Quaoar, Gong, and Sedna. Less massive than the dwarf planets are the vast number of small solar system bodies, such as asteroids, comets, centaurs, meteoroids, and interplanetary dust clouds. The dwarf planet Ceres and many of these smaller bodies are located in the asteroid belt, between Mars's and Jupiter's orbit, while all other dwarf planets are members of populations of trans-Neptunian objects, which may be found in the Kuiper belt just outside Neptune or in the further scattered disk. Many objects in the solar system do not orbit the Sun directly and are instead natural satellites, commonly called moons, of larger bodies. These can be found throughout the solar system in sizes from planetary mass moons at their largest to much less massive moonlets at their smallest. The largest 2 moons, Ganymede of Jupiter and Titan of Saturn, are larger, though less massive, than the smallest planet, Mercury, while the 7 most massive, which includes Earth's moon, are more massive and larger than any of the dwarf planets. The solar system is one of the most remarkable natural structures known to humanity, a vast cosmic arrangement that has both shaped and been shaped by the fundamental laws of the universe. At its center lies the Sun, a massive sphere of plasma whose gravitational dominance holds together an intricate family of planets, moons, asteroids, comets, and countless smaller particles. This system, though appearing stable and orderly from a human perspective, is in reality a dynamic and evolving environment, governed by complex interactions that have unfolded over billions of years. Its origins trace back approximately 4.6 billion years to the collapse of a dense region within a giant molecular cloud composed primarily of hydrogen and helium. As gravity pulled this cloud inward, it began to rotate, flattening into a spinning disk known as a protoplanetary disk. Most of the mass gathered at the center, eventually igniting nuclear fusion and forming the Sun, while the remaining material gradually coalesced into larger bodies through collisions and accretion. In these early stages, the solar system was a chaotic and violent place. Dust grains collided and stuck together, forming larger aggregates that grew into planetesimals, which in turn collided to form protoplanets. This process, studied within planetary science, explains how the diverse array of objects we see today came into existence. Temperature gradients within the protoplanetary disk played a critical role in determining the composition of these bodies. Close to the Sun, where temperatures were extremely high, only metals and silicates could condense, leading to the formation of the rocky terrestrial planets, Mercury, Venus, Earth, and Mars. Farther from the Sun, cooler temperatures allowed volatile compounds such as water, methane, and ammonia to freeze, contributing to the formation of the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune. Between the orbits of Mars and Jupiter lies the asteroid belt, a region filled with rocky debris that never formed into a planet due to Jupiter's strong gravitational influence. Beyond Neptune stretches the Kuiper belt, home to icy bodies and dwarf planets such as Pluto, and even farther lies the distant and largely theoretical Oort cloud. These outer regions preserve some of the most primitive material from the early solar system, offering a window into its formation. The entire system is bound together by gravity, which governs the motion of planets and smaller bodies, while angular momentum ensures that the rotational and orbital patterns established during formation persist over time. Despite its apparent stability, the solar system is constantly changing. Planetary orbits evolve due to gravitational interactions described by orbital mechanics, and collisions between objects continue to reshape surfaces and alter trajectories. Moons add another layer of complexity, often functioning as dynamic worlds in their own right. Some, like Europa and Titan, exhibit features that make them candidates for harboring life, expanding the scope of astrobiology. Even small bodies such as comets and asteroids play crucial roles, occasionally delivering water and organic compounds to planets or posing impact threats. The Sun itself is not merely a passive center but an active force shaping the solar system. It emits a continuous stream of charged particles known as the solar wind, which creates a vast bubble called the heliosphere. This heliosphere extends far beyond the orbit of Neptune and acts as a shield against cosmic radiation. Its boundary regions, where solar wind meets interstellar space, mark the transition between our solar system and the broader Milky Way. These interactions remind us that the solar system is not isolated but embedded within a much larger cosmic environment. Energy from the Sun drives a wide range of processes across the solar system. On Earth, it powers climate systems, supports photosynthesis, and sustains life. This energy flow is governed by principles such as thermodynamics, which determine how heat is absorbed, transferred, and radiated. Differences in atmospheric composition and planetary conditions lead to vastly different outcomes, from the extreme greenhouse effect on Venus to the cold, thin atmosphere of Mars. These variations highlight the delicate balance required for habitability and underscore the uniqueness of Earth within the solar system. Magnetic fields also play a crucial role in shaping planetary environments. Earth's magnetosphere protects it from harmful solar radiation, preserving its atmosphere and enabling life to thrive. In contrast, Mars, lacking a strong global magnetic field, has lost much of its atmosphere over time. Tidal forces, another subtle but important influence, affect rotational dynamics and internal heating, as seen in the interaction between Earth and its moon. These forces illustrate how interconnected and dynamic the solar system truly is, with even small influences accumulating over vast time scales. The solar system has profoundly influenced human thought and culture. Early civilizations looked to the sky to understand their place in the universe, developing models that placed Earth at the center. This view was overturned during the Copernican revolution, which established the Sun as the central body and marked a turning point in scientific thinking. Since then, the study of the solar system has driven advances in astronomy and astrophysics, leading to technological innovations and a deeper understanding of the universe. In modern times, the solar system has become a focus of exploration and ambition. Space missions have provided detailed observations of planets, moons, and smaller bodies, revealing complex geologies and unexpected phenomena. Mars has become a primary target for potential human exploration, while the Moon is being reconsidered as a base for further missions. The possibility of mining asteroids and utilizing extraterrestrial resources is also being explored, reflecting a shift from observation to active engagement. These developments raise important questions about sustainability, ethics, and the future of humanity in space. The long-term future of the solar system is shaped by the evolution of the Sun. Currently in a stable phase, the Sun will eventually exhaust its hydrogen fuel and expand into a red giant, dramatically altering the inner solar system. Planets like Mercury and Venus may be engulfed, and Earth could become uninhabitable. Eventually, the Sun will shed its outer layers, leaving behind a white dwarf. This process, studied in stellar evolution, provides insight into the life cycles of stars and the ultimate fate of planetary systems. Throughout its existence, the solar system has acted as both a cradle and a laboratory for understanding the universe. It has preserved the history of its formation in its smallest bodies, demonstrated the complexity of planetary interactions, and provided the conditions necessary for life to emerge on Earth. At the same time, it continues to evolve, influenced by both internal dynamics and external forces from the galaxy. Its study bridges multiple disciplines, from physics and chemistry to biology and philosophy, making it one of the most comprehensive subjects of scientific inquiry. The solar system is far more than a collection of celestial objects orbiting a star. It is a dynamic, interconnected system that embodies the fundamental processes of the universe. From its turbulent beginnings in a collapsing cloud of gas and dust to its current state of structured complexity, it tells a story of creation, transformation, and continuity. Its influence extends beyond science, shaping human thought, culture, and ambition, while its future holds both challenges and possibilities. As humanity continues to explore and understand this cosmic neighborhood, the solar system remains a source of knowledge, inspiration, and potential, linking our existence on Earth to the vast and ever-expanding universe beyond. The solar system is not something humans use in a direct, everyday sense like a tool or machine, but its components and processes provide immense practical, scientific, and future-oriented benefits that deeply influence life on Earth. One of the most fundamental uses comes from the Sun, which supplies the energy necessary for life. Solar radiation drives climate systems, powers photosynthesis in plants, and supports ecosystems across the planet. Without this steady energy input, Earth would be a frozen and lifeless world, making the Sun the primary source of all natural energy cycles. The solar system also serves as a natural laboratory for advancing knowledge in fields like astronomy and astrophysics. By studying planets, moons, and other bodies, scientists gain insights into fundamental processes such as planetary formation, atmospheric dynamics, and geological evolution. These insights are then applied to understand distant exoplanets and the broader universe. For example, studying the greenhouse effect on Venus helps scientists better understand climate change on Earth, while examining Mars provides clues about planetary habitability and environmental shifts over time. Another important use lies in technology and exploration. Observing and navigating the solar system has led to the development of satellite systems that support communication, weather forecasting, and global positioning. Space missions to bodies like Mars and the Moon have driven innovations in robotics, materials science, and engineering. These technologies often find applications on Earth, improving industries ranging from healthcare to transportation. The challenges of operating in space environments push technological boundaries, leading to solutions that benefit everyday life. The solar system also offers potential resources for the future. Asteroids contain valuable metals such as iron, nickel, and even rare elements, while the Moon and Mars may hold water ice that could be used for life support and fuel production. This concept, often referred to as space resource utilization, could support long-term human exploration and reduce dependence on Earth's limited resources. As interest grows in establishing human presence beyond Earth, the solar system becomes a potential extension of human activity rather than just an object of study. In addition, the solar system plays a role in planetary defense. By studying objects such as asteroids and comets, scientists can identify potential threats to Earth and develop strategies to prevent or mitigate impacts. This practical application highlights how understanding the dynamics of the solar system directly contributes to protecting life on our planet. Beyond science and technology, the solar system has cultural and philosophical significance. It has shaped calendars, navigation, and early scientific thought, and continues to inspire curiosity and exploration. The shift from an Earth-centered view to a Sun-centered understanding, marked by the Copernican revolution, transformed how humans perceive their place in the universe. Overall, the uses of the solar system span energy, science, technology, resource potential, safety, and inspiration. While we may not use it in a direct mechanical way, it underpins life, drives innovation, and provides opportunities for the future, making it one of the most valuable natural systems humanity depends on. Thank you for watching this video.